Today's topic is about the 5 types of chemical reactions. You've already seen all 5 of these sort of shown a little bit, I guess, in Lab 19. You've seen examples of all of them, though we haven't written the equations for them just yet. And with this video and the observations that you made in the lab, you should have all that you need to get the equations complete as part of your lab before you hand it in, as well as being able to classify all of the reactions that we'll see throughout most of second semester as one of the 5 types of chemical reactions. I do want to note now, in case I forget to mention it again later, that there are occasionally going to be reaction equations that don't look like any one of these 5 main types necessarily. Often those are combinations of several of these put together or happening sort of one after the other, and we write kind of an overall equation that puts all those together. Or maybe there's just a reaction that doesn't quite fit under any of these headings. And that's quite okay. I won't usually give you any of those as a trick or anything to try to get you to make mistakes or see if I can confuse you. But if you see a reaction on occasion that doesn't seem to look like any one of the 5 types, that's okay. There are reactions outside of these. They don't just quite all fit nicely into these containers. So keep that in mind as you go. One thing to keep in mind though, and you should already have these in your notes, so you don't need to write them again if you do, but keep in mind that as we go through all these reactions, if you see any of these 7 diatomic elements mentioned as elements as part of a reaction, and they'll be quite common in certain types especially, that they need to be considered as diatomic elements, as twos, coming in pairs. So again, these non-metals, 7 non-metals across the bottom here, Cliff Hoburn, chlorine, iodine, fluorine, hydrogen, oxygen, bromine, and nitrogen, all come in pairs when they're in their elemental form. And you'll see in equations where they're in compounds and things, that doesn't always mean they're going to be in pairs, but when they're as elements, they should always be remembered as pairs. So these are the 5 types of reactions, and you don't need to list them all right now. I'll just kind of give them to you all as kind of a preview. You don't need to list them all in your notes at this point because you'll be taking a little bit of commentary on each of the 5 sections as we go. But we've got synthesis. Your book also calls that a combination reaction. Decomposition, single replacement, double replacement, and combustion. And I'll give you a little bit of information on each of those types. First of all, a synthesis reaction more or less means that you're taking 2 or more simpler substances and combining those into one more complex substance. So you're taking small parts and putting them into one bigger part, and that bigger one will in some way look more complicated than the parts that you were putting together to make it. Synthesis is part of lots of words that we use all the time, like photosynthesis, for example. And so photosynthesis is when the sun takes small, simple things like carbon dioxide and water, puts them together into something quite a bit larger, in this case sugar, using energy from the sun. So photosynthesis, the photo part meaning light, and the synthesis part kind of relating to what we're talking about here. Photosynthesis also makes oxygen, so it's not quite the same as the reactions that you'll see here, but that's kind of the idea, taking simple things and putting them together into more complicated ones. And here you see sort of the general equation. You should put these in your notes, these general equations. You should also use these to answer the essential question in Lab 19 that asks about general reaction equations. It looks more or less like A plus B yields sum AB. A and B could be elements or compounds. AB will always be a compound. And for example, we've got one reaction here where water and carbon dioxide are being combined into, in this case, carbonic acid. This is what happens when carbon dioxide is dissolved into water, whether it's being done in a pop or whether it's done in just being a glass of water sitting on your countertop. One of the reasons that a glass of water, if left out overnight, will start to taste sort of funny by the next day is that carbon dioxide is dissolving into it, and it starts to make the water slightly acid. It tastes a little funny. So in Lab 19, Part A, you've got an equation where magnesium and oxygen were combining. You put magnesium into the crucible. And we often think about magnesium plus heat as being our reaction for this. Heat shouldn't be part of your reaction equations as far as a reactant goes. Those should be substances. And so it's magnesium being heated, but in the presence of the other reactant, which is oxygen. Sometimes it's not what we put into the crucible or what we put into the beaker. Sometimes it's just what we don't stop from getting in there on its own. And in this case, that's oxygen. So what compound would magnesium and oxygen make if you put those 2 things together? Hopefully you'd come up with an idea of a compound called magnesium oxide. And then it's a matter of writing the formula for magnesium oxide correctly, MgO. Make sure to keep in mind as you're writing these formulas the same things you've done all along. Charges of +2 and -2 in this case give us a compound magnesium oxide, MgO. The other reaction you should put down for Lab 19, Part A, and those equation sections of the lab is the fact that magnesium is also combining with nitrogen. Most of the air you breathe, nearly 80% of it is nitrogen gas, and so that's also going to be combining with magnesium. Metals and nonmetals get along pretty well. We've talked about that with ionic bonding. And so the other reaction that you'll see happening in this particular lab is magnesium with nitrogen, and hopefully you'd be able to come up with the idea that that compound would be called magnesium nitride with a D. And so the formula for that, Mg3n2, magnesium a +2 cation, nitrogen a -3 anion put together gives us that formula. And again, you don't need to worry about balancing these right now. I may ask you to balance these before we hand the lab in, but you'll be getting balancing reactions either in class or in another video coming up this week. And so for right now, you don't need to worry about balancing them. But those are the reactions that you saw there in Lab 19, Part A. You'll also notice there's a room for a third equation as part of your lab. You can skip that one. That's a follow-up reaction that I don't like to fill in with you at this time because it's not a synthesis reaction necessarily, and it tends to confuse people. So let's leave that third reaction under Part A blank in your lab for now. In synthesis reactions, you're often going to be asked to figure out what the product will be called. You just did that with magnesium and oxygen, magnesium oxide, or magnesium nitride when nitrogen was involved. But when you have to work with a transition metal, there's often more than one choice for a cation's charge. You've seen this with things like Roman numerals throughout the whole semester. So when we worked with transition metals that have more than one oxidation number possible, you had to choose one. When you're making compounds out of those, generally speaking, you could choose any of the charges that are listed there and be legitimately correct. But for simplicity's sake, for the most part, I'll ask you as you're doing it, just so we can kind of all be on the same page and keep things somewhat simpler for the time being. Choose the bold-faced oxidation number when one is given, and as you're writing these equations, keep the diatomic elements in mind. So for example, if platinum was to combine with chlorine, platinum is a transition metal that has more than one charge listed. You can see on your periodic table that it has a +2 and a +4 listed. And so as I kind of indicate to you here, choose the bold-faced oxidation number when in doubt. You could choose the other one and be more or less correct, but my answer keys will usually be written with the bold-faced number in mind, just so we can kind of all be on the same page and get the idea anyway. So for platinum, because the 4 is bold, I've chosen platinum 4 as my cation in the compound, and that gives me a compound PtCl4 because of chloride's -1 charge. So platinum 4 chloride, we would call that if we were writing out the word equation instead. Decomposition is our second kind of reaction. Decomposition is a term you hear in all kinds of gross places like rotting food and decaying flesh on shows like CSI Miami. You'll hardly ever see an episode of CSI Miami where Horatio doesn't take his dark sunglasses off over the scene of some gruesome crime, or where the pathologists are there crouched down over a body that's been rotting in the sun for a day or something. Decomposition is a common word in all kinds of places, and decomposing more or less means the same thing throughout all those uses. In this case, and in those cases, it usually means something complex is breaking down into some simpler stuff. In the case of a rotting piece of fruit, or more gruesomely, a decaying body or something on a crime show, flesh, tissues, proteins, muscle fibers, those are all very complicated substances, and as they break down into simple things. Most often, most disgustingly, the smells of rotting things, whatever they might be, are gases that are being produced, and they're very simple compounds often compared to the original stuff, the original tissue. In lab, we won't be breaking down any living tissues necessarily, but the same idea applies. A single substance that's more complicated breaks down into two or more simpler ones, and the general equation for that is CD, some compound CD, breaking into C and D. Again, C and D could be elements, they could be compounds, they could be one of each. Water can be broken down into its two constituent elements, hydrogen and oxygen. And keep in mind with these and all equations that those are diatomic elements, and so hydrogen and oxygen would both be followed by a 2. Water breaks down into hydrogen gas and oxygen gas, and you can do this as simply as a glass of water with a little bit of salt maybe, and a 9-volt battery with 2 wires leading off of it. You can easily see bubbles forming off the end of the wires. On one wire will be the hydrogen, on the other will be the oxygen. We can do this in lab and actually collect the gases and see how much of each we're getting, and we can work with that as a problem later on this semester. Another example comes from Lab 19, and in Lab 19, this is Part B, you took the green copper carbonate, it was copper 2 carbonate, and heated it. Again, we don't put heat in there as a reactant, but we did heat it to make this happen. Most decomposition reactions need some heat, not all of them, but many of them do. Many of them need a lot of heat. And copper carbonate broke down in that lab section into carbon dioxide gas. which you hopefully recognize because of the lime water test, and copper 2 oxide. Now notice here, we're not quite as simple all the time as just saying, okay, I took CO2 out of there, and that leaves me the copper and one of the oxygens. It worked out this time. It does not always work out that simply. You can see up above with water that if you take two H's off of water, that leaves you a single O, not the O2. So it doesn't always work just to take the two H's off and whatever's left is the other stuff. It's not quite that simple. But in Lab 19, that was our equation. In that case, you can see one compound broke down into two simpler compounds. Another good example of decomposition. A single replacement reaction is a fairly simple idea for the most part. Important to keep in mind that one element will always replace another. And so as we look at an equation for single replacement, you'll see one element kind of bumping the other one out of a compound. It's important to keep in mind that metals will always replace other metals, and nonmetals tend to replace other nonmetals. As a side note, hydrogen acts like a metal. Hydrogen, as you found in many compounds, including all of our acids, takes on a positive charge when it's in many compounds. That would make it more like a metal, because metals tend to be cations, and hydrogen sort of acts like one. So hydrogen acts like a metal and is replaced by metals quite often. In fact, that's what you did in Lab 19. Our general equations, there's actually two of them, can look kind of like this. E plus Fg, some element E, plus some compound Fg, will yield a compound Eg plus the element F. And the reason that those are specifically colored the way they are is that the metals, in this case, are colored in blue, and the nonmetal G is colored in red. And so as E comes in, it'll bump out the F, the metal, and not the G. It'll take the place of the element that it is most like. In the second equation, you can see that that same compound, Fg, is still around, but now we've put it with a different element, H, which you can see is red, and so we want to think about H as a non-metal. And so H will replace G, whatever the element that happens to be, because H is a nonmetal and G is a nonmetal anion, and so it'll take the place of G and bump it out. Think about this if you've ever been to a wedding in southwestern North Dakota. At least that's where I've gone to a lot of weddings in my life. Many North Dakota weddings have what's called a dollar dance. And in the dollar dance, there's a bride and a groom out there on the dance floor, and people line up with money and give it to them as a donation or as a gift to get them started on their way or pay for their honeymoon or something. And as a reward for giving them a dollar or $5 or $10 or $20 or whatever you want to be generous and give, you get a minute to dance with the bride or groom. And so what you'll have is the bride out there dancing with some gentleman, and the next guy will put money in the hat, and he'll go up and bump the guy out and dance with the bride for a minute. And then the next guy will come and bump that guy out and dance with the bride, and the bride just kind of stays there. And one guy after the other bounces out the previous one and takes his place, cuts in, if you will. The classic 1950s, 60s movie scene where someone asks if they can cut in on the couple. And if a gentleman comes over and asks if he may cut in, if you're so inclined, you can say yes, and you can let him dance with the girl you're dancing with. Well, in this case, E and F, for example, might be two guys, and E comes in and bumps F out of his place in the compound and dances off with G, and F is left alone, sadly by himself, at the punch bowl perhaps or something. In the second example, you can see H is cutting in on G, so maybe now the red ones are the girls, and H is cutting in and taking G's place. So H dances off with F, and G is left by herself in the corner by the punch bowl. Maybe, I don't know, finding a different element somewhere there to hook up with for later, I don't know. In our example from the lab, you put zinc metal in the presence of hydrochloric acid. And zinc is a metal, of course. Hydrogen acts like a metal. And so what happened was zinc took the place of hydrogen, bumped it out of the compound, and so zinc went with chloride, and hydrogen was left out by itself. Now notice here, hydrogen is a diatomic element, so it's got a 2 behind it. And also notice that in the compound zinc chloride, it's ZnCl2 because of zinc's +2 charge and chloride's -1 charge. That formula would be ZnCl2. Watch those charges as you're writing every compound throughout any equations at all when you're figuring out what the products will be. You can see here the metals, or the metal-like hydrogen, are both in blue, and chlorine is in red. So that's a single replacement reaction. So who can bump out who? There's rules to this as we go. An activity series is a ranking system that tells us which elements can replace which others and which cannot replace the others. In other words, if one element replaces another, it can't be that the other one will turn right back around and replace the first one again, because if it works both ways, then we'd have constant kind of chaos. In other words, there's a pecking order. in terms of how these reactions end up looking. There's sort of what we call a series or a ranking that puts the elements in order. Who can replace whom in the reaction series? And we see that as our guide to allowing reactions to happen or not. Okay? If I'm higher on the activity series than you, then I can bump you out of your compound and cut in and take your place. If I'm not higher than you, then I can't replace you. So it's sort of a pecking order, and it always works. It always holds true. What you see here is an activity series, a list of some of the metals, and I'll be giving you a copy of this if I haven't already, on a blue page usually, that lists all of these metals from first to last in this order. If you look at this list, more or less what this means is that lithium at the very top of the list could replace every other metal below it on the list because it's ranked number 1. Think about this like a basketball poll where the number 1 team could beat the number 2, 3, 4, every other team below it in the ranking. But the teams below could not knock off the number 1 team. Now, of course, in basketball and other things, that never holds true. Number 1 always loses eventually, it seems. But in the chemical world, in the chemistry world, the number 1 element, lithium, is never beaten. Lithium always wins. And so the other ones can't replace him. If we went to, say, aluminum further down the list, aluminum could replace any elements below it, manganese, zinc, chromium, and so on. But it could not replace these elements above it. Lithium, potassium, barium, calcium, sodium, magnesium, those would all be safe and would be ranked higher than aluminum. It's also important to remember that an element cannot replace itself. Aluminum can't beat aluminum, it's more or less a tie. And so you can't think about aluminum replacing itself in a reaction. That doesn't make any sense. Who's faster, me or me? That doesn't make a bit of sense. That's it for this section. We'll pick it up with double replacement reactions and combustion on the next video. So we'll catch you there.